A giant cosmic city floats over 300 million light-years away. This is the Coma Cluster, a sprawling metropolis of thousands of galaxies bound together by gravity. It is one of the most massive structures we have ever found, and it holds secrets that defy everything we think we know about how the universe works. By the end of this journey, you will understand 25 of its most profound and unsettling mysteries. We will confront ghostly galaxies made almost entirely of shadow, and question why the very heart of this cluster seems to disobey the laws of physics. What does it feel like to look into the abyss and have it look back with 1,000 unanswered questions? But the first and most fundamental mystery is not what we see, it is what we cannot see. The Coma Cluster has a secret. It is far heavier than it looks. The galaxies within it, like bright islands in a dark sea, are moving at tremendous speeds. They are whipping around the cluster's center, orbiting so fast that the gravity from all their combined stars and gas should not be strong enough to hold them together. According to everything we understand about gravity, these galaxies should have flown apart long ago, scattering into the lonely void of space. The only explanation is that something else is here, something invisible and immensely heavy, providing the extra gravitational glue to keep the entire structure intact. Astronomers call this the missing mass problem. They can measure the speeds of hundreds of galaxies within the cluster, a chaotic dance of velocities known as the velocity dispersion. This data tells them precisely how much total mass must be present to create that motion. When they then add up the mass of everything they can see, every star, every wisp of glowing gas, every speck of dust, the numbers come up catastrophically short. The cluster behaves as if it contains 5, maybe even 10 times more matter than is visibly accounted for. Further proof comes from a phenomenon called gravitational lensing. The immense gravity of the cluster warps the very fabric of space-time around it, bending the light from even more distant galaxies far behind it. By studying these distorted, stretched images of background galaxies, scientists can literally map the cluster's total mass distribution. That map reveals a vast, massive halo that perfectly aligns with the motions of the galaxies, yet emits no light of its own. This is the ghost in the machine, the unseen architecture that holds the cosmic city together. This invisible substance, which we now call dark matter, is the Coma Cluster's first and most profound enigma, the shadowy foundation upon which all its other mysteries are built. This missing mass is not the only ghost haunting the Coma Cluster. Drifting silently among its brighter galactic neighbors are phantoms, vast and faint, that defy our expectations of what a galaxy should be. They are called ultra-diffuse galaxies, and they represent the second great mystery of this cosmic city. The most famous of these, discovered right here in Coma, is known as Dragonfly 44. Picture, if you will, a galaxy the size of our own magnificent Milky Way, a sprawling disk spanning over 100,000 light-years. Now take away 99% of its stars. What remains is Dragonfly 44, a ghostly silhouette so faint it was missed by astronomers for decades, a whisper of starlight against the black. The mystery is not just its dimness but its survival. The Coma Cluster is a violent, crowded environment. Galaxies whip past each other at millions of miles per hour, and the gravitational tides between them are ferocious. A galaxy as large and as fragile as Dragonfly 44 should have been shredded long ago, its meager stars scattered like dust in a hurricane, yet there it floats intact. How does such a delicate structure endure in such a brutal place? The leading theory points back to the shadow we just discussed, dark matter. Scientists suspect that Dragonfly 44 and others like it are not actually fragile at all. They may be encased within an incredibly massive, incredibly dense halo of dark matter. This invisible armor would act like a gravitational shield, protecting the sparse stars within from being ripped away by the cluster's chaotic forces. In this scenario, the galaxy is like a single tiny light bulb hanging in the center of a massive, invisible bank vault, its dark matter halo providing the immense weight and stability needed for survival. An alternative idea suggests a different, more tragic history. Perhaps these ultra-diffuse galaxies were not born this way, but were made. They could be the stripped and ravaged corpses of once normal galaxies that ventured too close to the cluster's core. Over billions of years, repeated gravitational encounters may have robbed them of nearly all their gas and most of their stars, leaving behind only a bloated, faint remnant of their former selves. Whether they are born dark or made dark, these phantom galaxies force us to ask a deeper question. Is the Coma Cluster not just a collection of galaxies, but also a cosmic graveyard filled with the faint, lingering echoes of structures that failed to shine? The ghostly galaxies are not the only ones that have stopped living vibrant lives. If you look across the vast cityscape of the Coma Cluster, you will notice a striking uniformity in color, a sea of dull, reddish gold. This is the third great mystery, the problem of the red and dead galaxies. Within this dense cosmic environment, the majority of the large galaxies are elliptical in shape, smooth and featureless, and they glow with the cold, ruddy light of ancient stars. They are cosmic retirement homes, places where star formation ceased billions of years ago. The puzzle is not just that they are old, but that their star-forming factories were shut down with such brutal and universal efficiency. In the quieter suburbs of the universe, like our own local group, galaxies of all ages and colors mix together. But in Coma's dense urban core, the vibrant blue spirals, rich with the gas needed to birth new stars, are almost entirely absent. Something happened here long ago that systematically and permanently extinguished the spark of creation. One of the prime suspects is a process as violent as it is vivid called ram pressure stripping. The space between galaxies in a cluster is not empty. It is filled with a superheated, thin soup of gas known as the intracluster medium. As a spiral galaxy falls into the cluster for the first time, plunging through this searing plasma at thousands of kilometers per second, it experiences a cosmic headwind of unimaginable force. This wind acts like a torrential blast, physically scouring the galaxy's own reservoir of cold gas, the raw fuel for new stars right out of its disk. You can picture a dandelion seed head being held out of a car window at highway speed, watching all the delicate seeds get ripped away by the rushing air. That galaxy is left gas poor and starved, its future stolen in a single traumatic passage. A slower, more insidious process is known as strangulation. Here, the galaxy is not violently robbed but subtly cut off. As it enters the cluster's gravitational influence, the vast halo of hot gas that typically surrounds a galaxy, its future fuel supply, is stripped away. The galaxy continues to burn through its remaining internal gas, forming stars until it simply runs out of fuel. With no fresh deliveries from the outside, the stellar production line grinds to a permanent halt. It is a slow death by cosmic starvation. Then there is galaxy harassment, the death by 1,000 cuts. In the crowded downtown of the cluster, galaxies are constantly brushing past each other, their gravitational fields tugging and distorting one another. These repeated close encounters can shake up a spiral galaxy's orderly structure, destabilizing its gas clouds and either triggering a burst of frantic star formation that quickly consumes all the fuel, or flinging the gas out into the void entirely. The galaxy is left perturbed, puffed up into a more elliptical shape, and utterly depleted. The true mystery is that all these processes likely worked in concert, a multi-front war on star formation that left Coma's galactic population uniformly red and dead far earlier than in less dense parts of the universe. This raises a profound question. Was the Coma Cluster always destined to become a cosmic museum, a collection of fossilized galaxies whose best days were over before Earth even formed? The map of mass created by gravitational lensing reveals something even stranger than just a missing ingredient. When astronomers trace the distorted arcs and multiple mirrored images of galaxies far behind the Coma Cluster, they find that the map does not always line up neatly with the map of glowing matter. The dark matter halo, it seems, is not a perfectly smooth and uniform cloud. The lensing distortions suggest it might be lumpy, clumpy, or distributed in ways that our standard models of cold dark matter do not perfectly predict. Think of it like looking at the shadow of a tree cast by a streetlight. If the tree has a smooth, solid trunk, you would expect a single, dark shadow. But what if the shadow appears broken into several distinct, shifting patches? That would imply the tree's structure is far more complex, with gaps and dense knots hidden within its silhouette. These gravitational lensing anomalies are the cosmic equivalent of that broken shadow. They hint that dark matter might interact with itself in subtle ways we do not yet understand, perhaps through forces beyond gravity. This has fueled a deep debate in cosmology. The traditional model assumes cold dark matter, meaning its particles move slowly and interact with each other and with normal matter only through gravity. It is aloof and ghostly, but the clumpiness suggested by some Coma observations has led other scientists to propose alternatives like self-interacting dark matter. In this model, dark matter particles could occasionally bump into each other, scattering like subatomic billiard balls. This self-interaction would smooth out the densest clumps in the halo over time, potentially creating a distribution that better matches certain lensing patterns. The Coma Cluster, with its immense gravity and clear lensing effects, acts as a giant natural laboratory for testing these ideas. Each distorted arc of light is a clue, a forensic imprint left by the invisible on the visible. The ongoing analysis asks a fundamental question: is the dark matter holding this cosmic city together a sea of silent, non-interacting particles, or is it a dynamic substance with a hidden, complex life of its own? The answer could rewrite the rules for how all structures in the universe form and evolve. Deep within the heart of the Coma Cluster, another kind of ghost makes its presence known, not through gravity or faint starlight, but through a whisper on the radio. This is the fifth mystery, the origin of the colossal diffuse radio halo. Enveloping the cluster's central region is a vast, cloud-like veil of radio emission, stretching over 10 million light-years across. It is not tied to any single galaxy, but rather floats within the space between them, a faint echo of something immensely powerful. This radio whisper is a specific kind of light called synchrotron radiation. It is the signature of electrons, not just any electrons, but particles whipped to nearly the speed of light, spiraling wildly around magnetic field lines that are woven through the cluster's emptiness. The very existence of this halo tells us two astonishing things. First, the space between galaxies in Coma is not a true void. It is threaded with invisible magnetic fields, a cosmic magnetic tapestry. Second, something in that space is acting as a natural particle accelerator, more powerful than any machine on Earth, launching electrons to these extreme energies. But what is that cosmic engine? The identity of this particle accelerator is one of the cluster's most heated debates. One leading theory points to the violence of galactic mergers. When two giant galaxies collide within the cluster, the titanic shockwaves from the impact could ripple through the intergalactic gas, accelerating electrons in their wake like surf on a cosmic shore. Over billions of years, countless mergers could have filled the cluster's core with this sea of high-energy particles. Another idea suggests the acceleration comes from the cluster's own slow, monstrous growth. As the Coma Cluster continues to feed, pulling in fresh gas and smaller groups of galaxies from the cosmic filaments around it, this constant accretion creates immense turbulence in the hot plasma between galaxies. This churning, chaotic motion could generate waves and shocks that continuously re-accelerate electrons, keeping the radio halo alive. A third, more ghostly possibility looks to the past. The diffuse glow we see today might be the fading remnant of activity that happened long ago. Perhaps in the cluster's youth, many of its galaxies hosted voracious supermassive black holes at their centers, blazing as active galactic nuclei. These cosmic beacons would have blasted out jets of high-energy particles into the cluster environment. Even after the black holes quieted down and the jets shut off, the particles they expelled could still be spiraling in the magnetic fields, their faint synchrotron glow lingering like the afterglow of a long-extinguished fire. Each theory paints a different picture of the cluster's history. Is the radio halo the product of sudden, violent catastrophes between galaxies? Or is it the signature of the cluster's steady, breath-like growth? Or is it the accumulated ghost light of ancient monsters, their roars faded to a permanent whisper? This invisible radio cloud forces us to listen to the echoes of the Coma Cluster's most energetic and most mysterious past. That faint radio whisper is not the only high-energy mystery echoing from the Coma Cluster. From the direction of this cosmic city, we have detected bullets fired by the universe itself, particles of such staggering power they defy comprehension. These are ultra-high-energy cosmic rays, and their potential connection to Coma is the sixth great puzzle. A single one of these particles, often a solitary proton, arrives at Earth carrying as much kinetic energy as a professionally thrown baseball. All that unimaginable force is packed into a subatomic speck smaller than an atom. The mystery is not just their existence, but their origin. What cosmic catastrophe could possibly accelerate a single particle to such an insane velocity? The Coma Cluster, with its immense gravitational fields and violent history, is a prime suspect for harboring such an extreme engine. Yet tracing these rays back home is a detective story with a fundamental flaw. Cosmic rays are not light, they are charged particles. As they streak across the universe, they are bent and deflected by the magnetic fields that thread the space between galaxies. By the time one finally reaches our detectors, its path is so scrambled it is like trying to find the source of a single, specific raindrop in a hurricane by looking at where it hit the ground. The direction it came from is almost completely lost, so we are left with probabilities and candidates within the general vicinity of the cluster. One leading suspect is the fury of an active galactic nucleus. Imagine a supermassive black hole at the heart of a galaxy, feeding voraciously. As matter spirals in, it can launch jets of plasma moving at nearly the speed of light from its poles. These jets are natural particle accelerators on a galactic scale, and it is conceivable they could fire off the occasional proton with that unbelievable ultra-high energy. Another candidate arises from the cluster's very formation. As the Coma Cluster grew, pulling in vast rivers of gas from the cosmic web, the collision of these inflows would have generated colossal shock waves larger than entire galaxies. These shocks could ripple through the cluster for eons, and in their turbulent wake, they might accelerate particles to these extreme velocities over immense distances. But there is a third, far more exotic possibility that ties back to the cluster's dominant ghost. What if the source is not a violent event but a quiet decay? Some theories propose that dark matter is not a single type of particle but a spectrum. Among them could be super-heavy dark matter particles, relics from the universe's first moments, with masses far beyond anything we can create in our particle colliders. If these hypothetical particles are unstable, they could very slowly decay, and in their decay, release a tremendous burst of energy that manifests as an ultra-high energy cosmic ray. The immense gravitational well of the Coma Cluster, with its unparalleled concentration of dark matter, would be the perfect place for such rare decays to occur. So we face a profound question. Are these cosmic bullets the smoking gun from a specific, violent event we can point to, like a black hole's jet? Or are they the faint, random death throes of the invisible matter that shapes the universe itself? Each ultra-high energy particle that arrives from the direction of the Coma Cluster is a messenger, but its letter of origin is written in a code we have not yet fully broken. Between the galaxies of the Coma Cluster, a faint cosmic mist hangs in the darkness. This is the seventh mystery, the enigma of the intracluster light. It is not the glow of gas, but the combined starlight of billions of individual suns that have been ripped from their home galaxies and now drift untethered in the vast spaces between. They are cosmic orphans, a ghostly population that makes up a significant portion of the cluster's total brightness. Yet when astronomers study the color of this faint, diffuse glow, they find something deeply puzzling. It is bluer than it should be. In the harsh, empty realm between galaxies, we expected to find only ancient red stars, the old survivors of galactic collisions. The blue tint, however, whispers of youth. Blue stars are massive, hot, and short-lived. They burn through their nuclear fuel in just millions of years, a blink in cosmic time. Their presence means that somewhere, somehow, new stars have been born recently in the most inhospitable place imaginable, the near-perfect vacuum of intergalactic space. This discovery shatters a fundamental assumption. We thought stars could only form within the dense, nurturing clouds of gas inside galaxies. The intracluster medium is supposed to be a graveyard, not a nursery. So how did these blue stars get there? One possibility is a story of theft and rebirth. When galaxies collide or brush past each other in the cluster's crowded core, colossal tides of gas are pulled out into long, streaming bridges called tidal tails. Within these drawn-out rivers of stolen material, pockets of gas might become dense enough to collapse under their own gravity, sparking a burst of star formation far from any galactic disk. These stars would then be born into a life of exile, shining briefly before dying and enriching the void with new elements. Another, more violent idea involves ram pressure stripping, the same process that shuts down star formation in galaxies. As a spiral galaxy plunges through the cluster's hot plasma, its cold gas is not just stripped away quietly. The process can be chaotic and compressive, squeezing the gas as it is torn out. This sudden pressure might trigger the cloud to fragment and collapse, forming stars directly in the galactic wake, like sparks flying from a piece of metal dragged across a grindstone. The stars would then be left behind, a trail of blue embers marking the galaxy's tragic path. There is a third, more serene possibility. Perhaps some of these stars were not born in the void at all, but were gently nudged out long ago. Small groups of stars, known as globular clusters, which orbit in the outskirts of galaxies, could have been gravitationally shaken loose during close encounters. While globular clusters themselves contain old, red stars, their disruption could mix populations in a way that affects the average color we see. Yet the blue signature remains a stubborn clue that simple disruption cannot fully explain. The existence of this young, intracluster population forces a profound rethink. It suggests that the space between galaxies is not a static backdrop, but a dynamic and occasionally fertile frontier. The Coma Cluster is not just destroying galaxies, it might also be using their scattered remains to paint the darkness with unexpected, fleeting points of blue light. What other secrets of creation are hiding in the deepest voids? The ghostly blue stars drifting between galaxies are not the only anomalies of scale within the Coma Cluster. Deep within the hearts of its ancient elliptical galaxies, astronomers have found monsters that break the cosmic rules. These are the eighth mystery, the overmassive supermassive black holes. In most of the universe, there exists a tight and predictable relationship between a galaxy's central black hole and the dense bulge of stars at its core. The bigger the bulge, the bigger the black hole. It is a cosmic handshake that suggests their growth is intimately linked, but in the Coma Cluster, that relationship shatters. Here, the black holes are too big, like a massive engine crammed into a small car's frame. They are cosmic outliers, behemoths that outweigh what their galactic homes suggest they should be. This discovery forces a fundamental question. Did these black holes grow too fast, or did their galaxies somehow stop growing too soon? The dense, violent environment of the Coma Cluster provides two compelling and unsettling possibilities. The first is a story of gluttonous early growth. In the cluster's formative years, when it was a bustling, gas-rich protocluster, the central galaxies at its heart may have had first access to a veritable feast. Vast rivers of cold gas from the cosmic web could have funneled directly into their cores, feeding the nascent black holes at a breakneck pace. This rapid, runaway accretion would have allowed the black holes to balloon to enormous sizes before the harsh realities of cluster life set in. Imagine a sapling in a rainforest clearing that grows to a giant before the canopy closes overhead, stunting everything else around it. The black hole became a giant early, and its host galaxy's growth was later stunted by the cluster's fierce environment. The second possibility is a history written in collisions. The Coma Cluster is a galactic demolition derby. Over billions of years, its largest galaxies have cannibalized countless smaller ones in a process called galactic mergers. When two galaxies merge, their central black holes eventually sink to the new core and merge as well. In this dense environment, a dominant galaxy could have undergone multiple major mergers, each one adding another black hole's mass to its own central monster. The black hole grows through a diet of its peers, becoming overmassive through pure accumulation. Meanwhile, the galaxy's stellar bulge, while enlarged by the mergers, may not grow as efficiently, especially if the swallowed galaxies were gas-poor or if the merger process puffed the stars out into a more diffuse halo. The result is a black hole that is disproportionately heavy for the starlight that surrounds it. This mystery cuts to the heart of cosmic evolution. Are we looking at black holes that won a cosmic lottery of early feeding, or the accumulated trophies of a relentless, cluster-driven war of attrition? The answer rewrites the story of how the most powerful objects in the universe grow up in the busiest neighborhoods. The monstrous black holes at the heart of Coma's galaxies are not the only things starving in this cosmic city. The entire central region suffers from a profound and puzzling drought. This is the ninth mystery, the baffling absence of cool gas in the cluster's core. In many other massive clusters, the superheated plasma between galaxies should, over billions of years, slowly radiate away its energy, cool down, and condense into vast rivers of cold gas. This gas would then flow inward toward the cluster's heart, providing a fresh fuel supply to reignite star formation in the central galaxy, creating what astronomers call a cool core. It is a natural cosmic cycle, a form of precipitation where the rain is liquid star fuel. But in the Coma Cluster, that rain never falls. Its core remains uniformly hot, a searing, relaxed state where the gas shows no signs of condensing. The central giant galaxy, known as NGC 4874, sits in a permanent drought cut off from the cosmic reservoir. Why has the cooling cycle here been so completely shut off? The leading suspect points to a cataclysm in the cluster's past, a trauma so violent it permanently altered its internal climate. Astronomers see clues that the Coma Cluster may have suffered a major merger between two nearly equal subclusters long ago. Picture two vast clouds of galaxies and plasma, each the size of a small cluster, slowly colliding and merging into one. The process would not be a gentle blending. It would be like stirring two pots of scalding soup together with a cosmic spoon, injecting immense turbulence and generating colossal shock waves that ripple through the combined gas for eons. This energetic upheaval would have reheated the entire central atmosphere, wiping out any delicate cool cores that had begun to form and thoroughly mixing the plasma to prevent new condensation. The merger essentially reset the cluster's internal thermostat to maximum, and the system has been too agitated to cool down ever since. The evidence for this is subtle but compelling. The distribution of galaxies in Coma shows two distinct overdensities, like two crowds that have not fully mingled, suggesting a past union. The hot gas itself, when mapped in X-ray light, appears remarkably smooth and symmetric, which is exactly what you would expect after a major merger has had time to settle and relax into a new hot equilibrium. It is the calm after a storm of unimaginable violence. This single ancient event may have sealed the fate of the core, ensuring it remained a hot, quiescent desert where star formation could not be reborn. The mystery deepens when we consider the black holes. In cool core clusters, the inward rain of gas often feeds the central supermassive black hole, triggering outbursts that heat the surrounding gas and regulate the cooling, creating a feedback loop. In Coma, that loop is broken. The lack of cool gas means the central black hole is starved and quiet, unable to produce the heating jets that might have further influenced its environment. The cluster is locked in a strange, hot stasis. This raises a haunting question. Did a single, defining collision billions of years ago determine the ultimate fate of every galaxy in Coma's downtown, condemning them to a permanent, heated retirement by stealing away the very possibility of a celestial spring? The hot, still core of the cluster is a testament to ancient violence, but that violence may have left another, more subtle imprint on the survivors. Look at the spiral galaxies that still cling to life in Coma's outskirts, and you might notice something strange about the way they spin. Their rotation axes, the imaginary poles around which they turn, seem to whisper of a forgotten order. This is the 10th mystery, the puzzling alignment of galaxy spin axes. In a truly random universe, these spirals should point every which way, like a crowd of spinning tops tossed onto a floor. Yet in the Coma cluster, studies suggest they might prefer certain directions, aligning with the invisible scaffolding of the cosmos itself or with the cluster's own hidden magnetic fields. This faint signal, if confirmed, would be a cosmic fingerprint, revealing the hidden forces that shaped these galaxies as they fell into the cluster's grasp. One profound possibility is alignment with the large-scale structure. The universe is not a uniform soup, it is a vast web of filaments and walls with great voids between them. The Coma cluster sits at a dense knot where several of these cosmic filaments meet. As galaxies flow into the cluster along these filamentary highways, they do not fall randomly. They are channeled like water flowing into a drain along specific grooves. This directed inflow could impart a preferred direction of spin. Imagine a ball floating down a winding river, the currents causing it to rotate in a particular way as it moves. Similarly, the tidal gravitational forces from the filament itself could torque a galaxy, setting its spin axis perpendicular to the direction of the flow. If this is true, then by measuring how a galaxy spins today, we could trace its entire cosmic journey, reading the memory of its multi-billion-year migration along a specific filament of the web. Another, more enigmatic idea involves the cluster's own magnetic personality. We know from the diffuse radio halo that Coma is threaded with a large-scale magnetic field. While incredibly weak by Earth standards, this field is coherent over millions of light years. As a gas-rich spiral galaxy plunges through this magnetized environment, the interaction could be subtle but persistent. The magnetic field might exert a gentle torque on the galaxy's ionized gas slowly, over eons, coaxing its rotation axis to align with the field lines. It would be a staggeringly slow dance, a magnetic whisper gradually guiding the spin of an entire island universe. The implications of either scenario are deep. They suggest that a galaxy's fate is not determined solely by the violent events within the cluster, but also by the conditions of its long journey to get there. The direction a galaxy spins could be a fossil record, preserving information about the cosmic flows that birthed it and the magnetic environment it traversed. This raises a haunting question about fate and memory in the cosmos. Are we looking at galaxies whose very spin is a scar, a permanent reminder of the path they took into this crowded city, forever pointing back toward the lonely cosmic highways from which they came? The faint blue stars and the strange alignments of spin are the echoes of a brutal journey, one that reshapes galaxies on a fundamental level. This brings us to the 11th mystery, the ultimate fate of stripped spiral galaxies. For a spiral galaxy like our own Milky Way, entering the Coma Cluster is like stepping into a cosmic wind tunnel. As it plunges through the superheated plasma between galaxies, it encounters that ferocious headwind known as ram pressure. The effect is both dramatic and devastating. The galaxy's own reservoir of cold, star-forming gas, which is only loosely bound by gravity, is not simply slowed down, it is violently stripped away. Astronomers call the result a jellyfish galaxy, named for the long, streaming tendrils of gas and young stars that are torn from its disk, trailing behind it like cosmic tentacles. You can almost see the agony of the process, the galaxy's lifeblood being ripped out into the void. In Coma, we have caught these transformations in action. One striking example is the galaxy known as NGC 4921. Observations show it with a classic, undisturbed spiral structure at its heart, but with enormous, faint plumes of hydrogen gas stretching out behind it for hundreds of thousands of light years. It is a galaxy caught in the act of being dismantled. The mystery is not the stripping itself, but what comes after. When the ram pressure has done its work and the galaxy's gas is entirely gone, what remains? Does the spiral transform into another type of galaxy entirely, or does some ghost of its original structure persist? The leading theory suggests these stripped spirals become lenticular galaxies. A lenticular galaxy is a cosmic hybrid, possessing a central bulge and a large, smooth disk of old stars like a spiral, but without the gas and dust to form new stars or the prominent spiral arms. It is a galaxy frozen in time, a disk that has run out of fuel. This seems a logical endpoint for a spiral that has had its gas removed but whose stellar disk was left relatively intact by the stripping process. The galaxy NGC 4860 in Coma is often cited as a potential example of this, a disk galaxy with very little ongoing star formation, possibly a former spiral now quieted. But the dense, chaotic environment of Coma offers another, more violent destiny. A gas-stripped spiral is not just passive, it is vulnerable. Without its gas, it may be more susceptible to the gravitational harassment of its many neighbors. Repeated, close encounters could puff up its stellar disk, randomizing the orbits of its stars and blurring away any remaining spiral structure entirely. Over billions of years, this process could transform it from a thin, ordered disk into a more amorphous, roundish elliptical galaxy. The final nail in the coffin might be a merger. If a stripped, weakened spiral collides with another galaxy, the violent union would completely erase its disk, creating a new elliptical and leaving no trace of its spiral past. So we are left with a profound question about identity and cosmic memory. When a galaxy loses the very material that defined its vibrant life, does it become something new, or does it remain a hollowed-out version of its old self, a fossilized disk silently orbiting the cluster core? The fate of these jellyfish galaxies is a mystery of erasure, asking us what, in the end, truly defines a galaxy's soul when its ability to create new stars has been stolen forever. Those stripped galaxies leave behind more than just orphaned stars. They contribute to an invisible force field that blankets the entire cluster. This brings us to the 12th mystery, the hidden origin of the intracluster magnetic fields. We know these fields exist because we can see their effects, like the diffuse radio halo that glows from electrons spiraling along their lines. But their very presence in the vast emptiness between galaxies is a profound puzzle. How did magnetic fields, which we typically think of as belonging to stars or planets, become so strong and widespread across millions of light years of near-nothingness? The space here is so thin that if you collected all its matter in a volume the size of the Earth, it would weigh less than a single breath of air, yet it is magnetized. To unravel this, astronomers use a clever tool called Faraday rotation. When polarized radio waves from a distant source pass through a magnetized plasma, like the intracluster medium, their polarization angle gets twisted. By measuring this twist across many different background sources, scientists can literally map the strength and structure of the invisible magnetic field the waves traveled through. The maps confirm the fields are there, but their origin story is lost in time. One compelling theory is that they were planted by the cluster's most energetic residents long ago. In the youth of the Coma Cluster, many of its galaxies likely hosted blazing active galactic nuclei with supermassive black holes powering colossal jets. These jets would have acted like cosmic fire hoses, injecting not just high-energy particles, but also magnetic fields directly into the intergalactic environment. Think of it like stirring iron filings into a jar of water, each jet seeding the void with a thread of magnetism. Over eons, the gentle motions and immense turbulence generated by galaxy mergers and cluster growth would have stretched, twisted, and amplified these seed fields, like a baker kneading strands of dough throughout the entire loaf. This process, known as turbulent dynamo action, could have taken weak, scattered fields and woven them into the coherent, large-scale tapestry we detect today. It is a story of inheritance and amplification, but there exists another, far more radical possibility. What if these magnetic fields were not made by galaxies at all, but are primordial? In this scenario, the fields were born in the extreme conditions of the universe's first fractions of a second, woven into the fabric of space-time itself during cosmic inflation or subsequent phase transitions. They would have been present everywhere from the very beginning, a fundamental part of the cosmic substrate. As gravity pulled matter together to form clusters, these weak, universal fields would have been dragged along and compressed into the spaces between galaxies, their lines of force squeezed together and intensified by the sheer collapse of structure. This idea suggests that magnetism is as ancient as matter, a ghostly relic from creation that now silently guides particles in the darkness. The debate between these two origins, the active galactic seeding versus the passive primordial inheritance, is more than academic. If the fields are primordial, they represent a fossil from the universe's birth, a clue to physics at energies we can never hope to replicate. If they were made by galaxies, they are a testament to the incredible power of black holes and mergers to shape not just stars, but the very emptiness between them. The magnetic fields of the Coma Cluster are thus a silent question written across the void. Are we seeing the accumulated legacy of ancient monsters, or the faint signature of the universe's first moments? Those magnetic fields are not just a passive backdrop, they are the canvas upon which the cluster's most violent history is written in fading light. Deep within the Coma Cluster, astronomers have found colossal ghosts, faint and vast structures that glow only in radio waves. These are the fossil radio lobes, the 13th great mystery. They are the remnants of ancient cataclysmic outbursts from supermassive black holes that once blazed at the hearts of galaxies but have long since fallen silent. These structures, sometimes called radio phoenixes, are the cosmic equivalent of finding the fossilized bones of a long-extinct leviathan, a testament to an era of unimaginable power that has now passed. The lobes themselves are bubbles or clouds of magnetized plasma, inflated millions of years ago by relativistic jets screaming from an active galactic nucleus. When the central black hole stopped its furious feeding, the jets shut off, and the brilliant radio emission from the fresh, energetic particles should have faded away into darkness within a relatively short cosmic time, perhaps a few tens of millions of years. Yet here they are, still glowing faintly. This longevity is the first part of the puzzle. How can these ghosts persist for so long after the engine that created them has died? The answer seems to lie in the restless environment of the cluster itself. The intracluster medium is not still. It is constantly being stirred by the slow, majestic motion of galaxies and the echoes of past mergers. This movement generates shock waves and turbulence that ripple through the hot plasma. When one of these shock waves passes through an old, fossil radio lobe, it acts like a cosmic defibrillator. The shock compresses the ancient magnetic fields within the lobe and re-accelerates the old, lingering electrons back to high energies, causing the entire structure to light up again in radio waves for a brief second life. It is a phoenix reborn from the ashes of its own corpse by the cluster's ambient violence. This process provides an incredible fossil record. By mapping the shapes and locations of these ghostly lobes, scientists can literally trace the history of shocks and turbulence in the cluster over hundreds of millions of years. A distorted, wispy lobe might mark the passage of a particularly powerful shock wave from a past galactic merger. The very presence of multiple such fossils at different stages of fading tells us that the cluster's core has been a site of repeated, energetic upheaval, not a quiet place. But this re-energizing mechanism raises its own profound questions. The shocks required are immense, and their sources are not always clear. Are we seeing the aftershocks of that single, defining cluster merger that heated the core, or the accumulated rumble from countless smaller galaxy collisions? Furthermore, the physics of how a diffuse shock wave can so efficiently re-accelerate particles across such a vast volume of space is not fully understood. It challenges our models of particle acceleration in environments of extreme but gentle pressure. These radio ghosts are therefore more than just fossils. They are active participants in the cluster's ecosystem. Their faint glow a direct response to the ongoing heartbeat of the Coma Cluster. They force us to ask, when we look at this ancient city of galaxies, are we seeing a settled retirement community, or a place still reverberating with the slow-motion echoes of its most traumatic past? These ghostly radio lobes are not the only scars left by ancient black hole outbursts. Etched into the very hot gas of the Coma Cluster, astronomers have found enormous empty spaces. These are the 14th mystery, the unexpected X-ray cavities. When we observe the cluster in X-ray light, we see a brilliant, smooth glow from the superheated plasma between galaxies. But within that glow, there are dark bubbles, regions where the X-ray emission suddenly drops. These are not holes in the gas, but immense cavities that have been carved out and inflated by the most powerful jets in the universe, fired from the supermassive black holes at the hearts of galaxies. The cavities are like cosmic blowholes, bubbles of relativistic plasma pushed into the hot gas, displacing it and leaving behind a void. Their existence tells a dramatic story, but their details hold deeper puzzles. The first mystery is their sheer scale. Some of these cavities can be hundreds of thousands of light years across, larger than many galaxies. They represent an almost unimaginable release of energy, as if a single object at the center of a galaxy detonated a bomb powerful enough to shove aside an ocean of million-degree plasma for cosmic distances. The energy required is staggering, often millions of times greater than a supernova. This forces us to ask just how efficient and violent the feeding process of a supermassive black hole can become. But the real enigma lies in what these cavities do, a process astronomers call feedback. The black hole, in its furious outburst, is not just creating a cavity, it is performing a cosmic regulatory act. As the bubble expands, it does work on the surrounding hot gas, pushing it outward and generating powerful shock waves that travel through the cluster. This process injects tremendous heat into the intracluster medium, like a colossal space heater turning on in the middle of the cluster's core. This heating is precisely the counterbalance needed to solve the cooling flow problem we discussed earlier. Remember, without some form of heating, the hot gas in the core should cool, condense, and rain down to form new stars. The black hole's outburst, evidenced by these X-ray cavities, provides that heat. It is a self-regulating cycle, a feedback loop of breathtaking elegance. When gas begins to cool and flow toward the central galaxy, some of it inevitably feeds the supermassive black hole. The black hole then awakens, launching jets that inflate cavities and heat the surrounding gas, which shuts off the cooling flow, which in turn starves the black hole, allowing it to go quiet again. The cycle then repeats over hundreds of millions of years. In Coma, however, this story is complicated by its hot, relaxed state. The cavities we see are likely fossils from past outbursts, their exact origins and timings difficult to pin down. Their distribution and size hint at a history of sporadic but incredibly violent regulatory events. Did a single, monstrous outburst from the central galaxy's black hole create the largest cavities, or are we seeing the accumulated work of several black holes in different galaxies over eons? Furthermore, the precise mechanics of how the energy from the jets is transferred so efficiently to heat the gas remains an active area of research. Is it primarily through the shock waves from the expanding bubbles, or through sound waves and turbulence rippling through the plasma? Each cavity is a fossilized echo of a black hole's roar, a permanent imprint of the moment it prevented its own galaxy, and perhaps the entire cluster core, from growing any further. They are the ultimate paradox, where the most destructive objects in the universe become the essential guardians of cosmic order, using violence to impose a lasting, heated peace. These immense X-ray cavities are monuments to the black holes that carved them, but the true scale of a giant galaxy's dominion is measured in a different kind of treasure. Swarming around the central giants of the Coma Cluster, like glittering satellites around a dark planet, are vast hordes of globular clusters. These are ancient, dense balls of hundreds of thousands of stars, each one a miniature galaxy in its own right. The 15th mystery lies not in their existence, but in their staggering abundance. A galaxy like our Milky Way possesses about 150 of these stellar fossils. The giant elliptical galaxies at the heart of Coma, however, are surrounded by thousands, sometimes even tens of thousands of them. This incredible population is a cosmic archive, and its very composition holds conflicting clues about how these galactic titans were built. The colors of these clusters tell a silent story. Globular clusters come in two broad families, distinguished by their hue. Red clusters are older, metal-rich, meaning they contain heavier elements forged in earlier generations of stars. Blue clusters are typically older as well, but are metal-poor, composed of more pristine, primordial material. In a giant elliptical galaxy, you find both in overwhelming numbers. So where did they all come from? One school of thought argues for a story of in situ formation, a grand birth alongside the host galaxy in the frantic early universe. In this scenario, the chaotic conditions during the galaxy's initial collapse and formation could have spawned thousands of these dense star clusters directly from the tumultuous gas clouds. They would be native to the galaxy, born from its own substance, with the redder, metal-richer clusters forming from gas already enriched by the earliest supernova in the galaxy's core. The sheer number would simply reflect the immense scale and violence of that primordial creation event. But the rival, and perhaps more compelling, theory paints a picture of galactic cannibalism and theft. This is the accretion model, as a giant galaxy sits at the gravitational center of the growing Coma Cluster. It acts as a devourer of smaller systems. Dwarf galaxies and other modest spirals that wander too close are torn apart by tidal forces. When such a satellite galaxy is destroyed, its own native globular clusters are not destroyed with it. Instead, they are stripped away and added to the giant's swirling halo, like pearls scattered from a broken necklace. Over billions of years, through countless mergers and disruptions, a giant galaxy can accumulate a vast collection of stolen clusters. This idea elegantly explains the mix of colors. The blue, metal-poor clusters likely originated in small, pristine dwarf galaxies that formed early and were later consumed. The redder clusters might have come from more massive, pre-enriched satellites or from the giant's own in situ population. The numbers themselves are the key evidence. The correlation is striking. The more massive the galaxy and the denser its environment, like the heart of Coma, the more globular clusters it has. This strongly suggests that the environment itself, the relentless process of galactic cannibalism fueled by the cluster's gravity, is the primary driver behind these immense swarms. Each globular cluster, then, could be a trophy from a long-digested companion, yet the mystery is not fully solved. Detailed studies of the motions and chemical compositions of these thousands of clusters are like doing a galactic census, trying to determine which are native citizens and which are immigrants. The data is complex, often pointing to a hybrid origin, a messy combination of both in situ birth and violent acquisition. This leaves us with a profound question about identity. When we look at a giant galaxy in Coma, crowned by its 10,000 glittering globular clusters, are we seeing the result of a singular, majestic genesis? Or are we looking at a cosmic collage, a Frankenstein's monster assembled from the devoured remains of an entire community of smaller galaxies? The answer is written in the ancient light of those swarming star clusters, a history of construction written in stolen jewels. The glittering swarms of globular clusters are not the only stolen treasures drifting through the Coma cluster. If you could see with eyes sensitive enough to detect the faintest starlight, you would witness a ghostly architecture of bridges and arcs connecting the galaxies themselves. These are the tidal tails and stellar streams, the 16th great mystery, and they are the scars of past collisions written in stars. They appear as faint, ribbon-like structures, long rivers of stars that have been pulled out from their parent galaxies during close gravitational encounters, stretching for hundreds of thousands of light years across the dark void. They are the cosmic equivalent of footprints in wet sand, preserving the direction and violence of an event that happened billions of years ago. By meticulously mapping these delicate structures, astronomers can perform a kind of celestial archaeology, reconstructing the dynamical history of the entire cluster. The length, curvature, and density of a stellar stream tell a precise story. They reveal the masses of the galaxies that interacted, the speed and angle of their passage, and even how long ago the encounter occurred. It is like finding the scattered pieces of a broken vase and, from their positions on the floor, deducing exactly how it fell from the shelf. In this way, the tidal debris around Coma's galaxies forms a living archive of the cluster's violent social life, a record of which galaxies danced together and which ones tore each other apart across cosmic time. Yet this beautiful forensic tool presents its own profound contradiction. The existence of these streams, especially in the cluster's dense core, is a puzzle of survival. The Coma cluster is a gravitational maelstrom. The same fierce tides that create these streams should, given enough time, also destroy them. As a stream orbits through the crowded cluster center, it is constantly buffeted by the gravitational pull of passing galaxies. These repeated, subtle tugs should pull the stream apart, dispersing its stars into the general haze of intracluster light within a relatively short time, perhaps a few 100 million years. The fact that we can still see so many distinct, coherent streams means one of two things. Either we are witnessing encounters that are surprisingly recent on the cosmic clock, a sign that the cluster's demolition derby is still actively ongoing. Or there is something about the cluster's gravitational landscape that is unexpectedly gentle, allowing these fragile structures to persist for much longer than our simulations predict. Perhaps the dark matter halos around galaxies are smoother or more extensive than we think, providing a protective cocoon that shields the streams from the worst of the disruptions. Another possibility is that the streams we see are not the original, delicate threads, but have already been stirred and thickened into broader, more robust arcs that are harder to erase. Each surviving stream is therefore a double mystery. It is both a clear record of a past event and a challenge to our understanding of the present environment. They force us to ask a haunting question about time and memory in this crowded city. Are we seeing the fresh wounds of an eternally violent place, or are we looking at the fading yet stubborn, ghosts of ancient cataclysms that the cluster has not yet managed to fully forget. Those stellar streams are the fading echoes of galactic collisions, but the true population of the smallest galaxies in the Coma Cluster tells a different story, one that returns us to the deepest ghost of all. The dwarf galaxies, the tiny, faint building blocks of the cosmos, are far fewer in number than our theories of dark matter predict. This is the 17th mystery, the dwarf galaxy problem, and it challenges our understanding of the universe on the smallest scales. According to the most successful model of cosmic structure, cold dark matter, the gravitational collapse of the early universe should have created an immense hierarchy of dark matter halos. For every massive halo that hosts a giant galaxy like our Milky Way, there should be hundreds, even thousands of smaller halos, each a potential cradle for a dwarf galaxy. When we look at the Coma Cluster, a place so massive it should have gathered these small halos by the multitude, we find a glaring discrepancy. The observed population of faint dwarf galaxies is only a fraction of what the dark matter simulations say should be there. So where are all the missing satellites? The first possibility is a simple matter of cosmic camouflage. Perhaps the dwarfs are there, but we just cannot see them. In the dense, bright core of the Coma Cluster, the faint, diffuse light of an ultra-faint dwarf galaxy could be utterly lost in the glare of its giant neighbors and the pervasive glow of intracluster light. It is like trying to spot a single, dim candle placed right next to a blazing stadium floodlight. Our telescopes, as powerful as they are, have limits. Surveys are constantly pushing deeper, and with each improvement we do discover more of these faint systems. But even accounting for these observational hurdles, the numbers still seem to fall short. This leads to the second, more profound explanation, a failure of galaxy formation itself. A dark matter halo is necessary to gather gas and form stars, but it is not sufficient. The process of turning a halo of primordial gas into a shining galaxy is delicate and can be thwarted in multiple ways. In the smallest halos, the gravitational pull is so weak that even a single supernova explosion from one of the first stars could blow all the remaining gas out into the void, permanently shutting down star formation. The halo would remain dark, a ghostly sphere of pure dark matter with perhaps only a handful of ancient stars, or none at all, rendering it virtually invisible to our telescopes. This idea of inefficient or even aborted galaxy formation could explain why we see so many predicted halos but so few actual galaxies. Then there is the brutal reality of the cluster environment, which offers a third, grim solution. The Coma Cluster is a cosmic shredder. As a small dwarf galaxy with its shallow gravitational well falls into the cluster, it faces an onslaught. The relentless tidal forces from the cluster's overall gravity and from close encounters with massive galaxies can literally tear a dwarf apart. Its stars are stripped away, joining the sea of intracluster light, while its dark matter halo, being more extended and robust, may survive longer as a free-floating shadow. In this scenario, the missing satellites are not missing, they have been murdered and dismembered, their stellar components dissolved into the background glow long ago. Their dark matter halos might still be there, invisible and untraceable, orbiting silently through the cluster. This mystery forces a fundamental choice about the nature of the universe's smallest structures. Are we looking at a cosmos where dark matter halos are abundant, but most are destined to remain dark, empty nurseries where stars never truly ignited? Or are we looking at a cosmic battlefield where the smallest galaxies are ephemeral, their brief flicker of light quickly extinguished by the violence of their surroundings? The dwarf galaxy problem in Coma is not just a census discrepancy. It is a direct test of how the invisible scaffolding of dark matter connects to the brilliant, visible universe we actually see. Amidst the faint streams and missing dwarfs, the Coma Cluster holds objects that defy simple classification. These are the ultra-compact dwarf galaxies, dense spheres of stars that shine with a puzzling intensity. They are the 18th great mystery, objects that blur the line between a star cluster and a true galaxy. Picture a ball of stars only about 200 light-years across, a speck compared to the 100,000 light-year span of our Milky Way. Yet within that tiny volume, it packs tens of millions of suns, shining with the combined light of a small galaxy. They are brighter than the most luminous globular clusters, yet far more compact than even the smallest dwarf galaxies. Their very existence in such numbers within Coma forces astronomers to ask a fundamental question: what are they? The leading theory is a story of cosmic decapitation. An ultra-compact dwarf may be the surviving heart of a larger galaxy that was violently stripped away. Imagine a small spiral or dwarf elliptical galaxy venturing too close to the cluster's core. The relentless gravitational tides from giant neighbors could, over time, peel away its outer layers of stars, leaving behind only the dense star-packed nucleus. This nucleus, now orphaned, would continue to orbit the cluster as an ultra-compact dwarf, a galactic core without its body. This idea is compelling because it connects to the fate of other stripped galaxies we have discussed, suggesting UCDS are the final, indestructible kernels left behind. But there is a rival hypothesis that points to an origin among the swarms of globular clusters. Could some UCDS simply be the most massive globular clusters ever formed? Perhaps in the intense environment of the early cluster, conditions were right to forge these monstrous star balls directly from collapsing clouds of gas. They would be born as giants, not made through destruction. The evidence for this comes from their internal chemistry. Some ultra-compact dwarfs show a mix of stars with a range of ages and metallicities, a complexity more typical of a galaxy that underwent multiple episodes of star formation, rather than a single burst like a classic globular cluster. This hints at a more intricate history. Coma, with its rich population of these objects, is the perfect place to test these ideas. By studying their motions, their colors, and the detailed spectra of their starlight, astronomers are trying to trace their lineage. Each one is a cosmic fossil, but is it the fossil of a devoured galaxy's heart or the fossil of an extraordinary birth? The mystery of the ultra-compact dwarfs challenges our categories, forcing us to wonder if the universe has a hidden middle ground between the largest star clusters and the smallest galaxies. A class of object we are only just beginning to recognize in the crowded streets of this ancient city. The chemical makeup of the hot gas between galaxies tells a brutal story of cosmic life and death. This is the 19th mystery, the hot gas metallicity puzzle. The superheated plasma filling the Coma cluster is not pristine hydrogen and helium from the Big Bang. It is laced with heavier elements, what astronomers call metals, forged in the furnaces of stars and scattered by their explosive deaths. By studying the X-ray fingerprints of elements like iron, oxygen, and silicon in this gas, we can read a forensic history of all the star formation and supernova that have ever occurred within the cluster's galaxies. But the story we are reading is full of contradictions. The first surprise is that the metals are not evenly mixed. You would expect, after billions of years of galactic collisions and the churning motion of the gas, that the chemical soup would be thoroughly blended like stirring cream into coffee. Yet the maps show patchiness. There are regions richer in iron, others where oxygen or silicon is more prominent. This unevenness is a frozen snapshot of incomplete mixing, suggesting that the violent events that injected these elements, the supernova, and the mergers that dispersed them happened relatively recently, or that the cluster's turbulence is less efficient at stirring the pot than we thought. Each patch is a chemical memory of a specific cataclysm that has not yet faded into the background. The deeper puzzle lies in the ratios of the elements themselves. Different types of stellar deaths produce different chemical signatures. Core collapse supernova, the explosions of massive, short-lived stars, are prolific factories for lighter metals like oxygen, neon, and silicon. Type 1, a supernova, which occur in binary systems where a white dwarf star is destroyed. are the primary cosmic producers of iron. By measuring the ratio of iron to oxygen in the intracluster gas, astronomers can, in principle, determine what fraction of the metals came from each type of explosion, revealing the historical balance of star formation in the cluster. But the numbers from Coma do not line up neatly with the predictions from our models of stellar evolution and galaxy growth. The observed iron abundance is often higher than expected for the amount of oxygen present. This iron excess is a profound clue. It suggests that over the cluster's long history, Type 1, a supernova, have been disproportionately efficient at polluting the intergalactic medium with iron. But why? One possibility points to the timing of events. Type 1, a supernova, happen with a significant delay, sometimes billions of years after the star formation that created their progenitor systems. In a dense environment like Coma, where an early, intense burst of star formation might have been quickly quenched, the delayed fireworks from these white dwarf explosions could have injected their iron into a gas reservoir that was already largely stripped from the galaxies, allowing it to mix directly into the intracluster medium. Meanwhile, the oxygen from the earlier massive star supernova might have been more tightly bound within the galaxies and lost to the void through different, less efficient processes. Another idea considers the brutal mechanics of stripping. When ram pressure scours a galaxy of its gas, it might not remove all elements equally. The enriched gas, bearing the metals from past supernova, could be more loosely bound and easier to strip than the primordial gas, leading to a selective enrichment of the intracluster medium. The very distribution of the elements becomes a map of violence. A region unusually rich in silicon might mark the path of a galaxy that experienced a recent burst of core collapse supernova just before its gas was torn away. A smooth gradient of iron decreasing from the cluster center might tell the story of how the giant central galaxies, through their long history of mergers and their prolific Type 1 supernova, have been the dominant polluters for the entire system. This chemical puzzle forces us to reconstruct a detailed timeline of death and dispersal. It asks, did most of the metals we see get expelled from galaxies early in the cluster's history, when star formation was rampant, or has there been a slow, steady leakage over eons? The uneven, ratio-defying gas of the Coma cluster is not just hot plasma. It is an unresolved chemical narrative, the still smoking evidence of trillions of stellar explosions whose final story we are only beginning to decipher. This chemical narrative is written in the very orientation of the cluster's most powerful residents. The giant galaxies that sit at the gravitational hearts of clusters like Coma, known as brightest cluster galaxies, hold a peculiar secret in the way they point. Their elongated shapes, their very axes of light, are not randomly oriented. They show a strange tendency to align with the overall egg-shaped distribution of the entire cluster. Even more astonishingly, when we zoom out to the scale of superclusters, these BCGs in neighboring clusters sometimes seem to point toward each other, as if acknowledging a shared lineage or bowing to a common master. This alignment is the 20th great mystery, a subtle signal written across hundreds of millions of light years that hints at forces shaping the cosmos on the grandest scales. Is this all just a remarkable coincidence, a frozen memory of how these giants were born? One compelling explanation takes us back to the cosmic web. Clusters form where the thickest filaments of dark matter and gas intersect. As matter streams into this knot along these specific highway-like filaments, it does not fall in from all directions equally. This anisotropic or directionally biased flow can set the spin of the collapsing protocluster and imprint a preferred orientation on the emerging structure. The central galaxy, forming from the gas that flows in most efficiently along the dominant filament, would naturally inherit this alignment, its shape stretching along the same axis as the cluster itself. Its orientation is a fossil, pointing back to the specific filament that fed its growth billions of years ago. but the alignments between BCGs in separate clusters within a supercluster suggest something even more profound. It implies that these filaments are not just local feeding tubes, but part of a coherent, large-scale architecture that can orchestrate alignment across vast distances. The entire supercluster may have a preferred direction of collapse or spin inherited from primordial density fluctuations in the infant universe. In this view, the alignment of BCGs is not a local story, but a chapter in a cosmological epic, tracing the flow of matter from near the dawn of time into the structures we see today. Yet there is a more dynamic and unsettling possibility. What if these alignments are not just frozen fossils, but evidence of ongoing influence? The gravitational pull from neighboring massive structures, like nearby superclusters or immense sheets of galaxies, could exert a persistent tidal force on a cluster. This force, gentle but operating over billions of years, could slowly torque the entire cluster and its central galaxy, coaxing it into alignment with the larger-scale mass distribution. It would be a staggeringly slow cosmic dance, where the most massive objects in the universe gradually turn to face the direction of greatest pull, a process called tidal alignment. This mystery forces us to confront the hierarchy of cosmic structure. Are the shapes of the universe's mightiest galaxies simply the end result of ancient, random flows, their orientations a silent testament to their birth conditions? Or are they still being subtly manipulated today, their pointers slowly shifting in response to the gravitational whispers of structures so vast we can barely map them? The aligned BCGs of the Coma Cluster and its neighbors are like cosmic compass needles. The question is, what invisible hand set them, and is that hand still gently turning them even now? The search for the sources of the universe's most brilliant flashes leads us straight into crowded places like the Coma Cluster. Fast radio bursts are millisecond-long eruptions of radio waves that pack the energy of hundreds of millions of suns, and while none have been definitively pinned to Coma yet, this dense cosmic city is a prime hunting ground for their elusive progenitors. The mystery of what creates these fleeting, colossal signals is one of modern astronomy's greatest puzzles, and the extreme environment of a massive cluster could be the perfect crucible. Theorists point to objects of almost unimaginable density and magnetic power, like magnetars, which are neutron stars with magnetic fields a trillion times stronger than Earth's, or the catastrophic mergers of two neutron stars. Such events require the most severe conditions in the universe, and the Coma Cluster, with its history of violent galactic collisions and crowded stellar populations, is a natural factory for these stellar extremes. It is a place where the chaotic dance of stars could easily lead to the encounters or cataclysms that might spark a fast radio burst, but the connection runs deeper than just a likely location. Each fast radio burst that passes through the Coma Cluster on its way to us carries a hidden imprint of the journey. As the burst travels through the sparse sea of electrons in intergalactic and intracluster space, its higher frequency waves arrive slightly before its lower frequency waves. This delay, called the dispersion measure, is a direct gauge of how much free electron fog the signal has passed through. If we could ever localize a burst originating from behind the Coma Cluster, or even within it, we could use that dispersion measure as a cosmic probe. By carefully subtracting the known contribution from our own galaxy and the general intergalactic medium, any excess delay could be attributed to the Coma Cluster's own intracluster medium, and even to the dark matter halos around its individual galaxies. In essence, a single split-second flash could act like a spotlight, illuminating the total amount of normal matter, the hot plasma and the stripped gas that is otherwise so difficult to map in fine detail. It could even test wilder ideas, like whether dark matter itself might interact with these radio waves in some minuscule way. So the search within Coma is twofold: a hunt for the cosmic monsters that might create these bursts, and a hope that the bursts themselves might finally reveal the hidden, ordinary matter woven through this ancient city of galaxies. A flash lasting less than a blink could, from a distance of hundreds of millions of light years, tell us more about the hidden structure of a cluster than years of traditional observation. The story of the Coma Cluster is not one of quiet assembly, but of a catastrophic collision written in the stars. This is the 22nd mystery, the unresolved subcluster merger history. To understand the giant we see today, we must rewind the cosmic clock and witness the slow-motion crash of two, or perhaps even more, smaller clusters into one another. The evidence for this ancient violence is everywhere, but piecing together the exact sequence is a detective story of galactic proportions. The first clue lies in the distribution of the galaxies themselves. When astronomers map their positions, they do not see a perfectly smooth, spherical swarm. Instead, they find hints of substructure, like two crowds that have not fully mingled. There is a noticeable concentration around the giant galaxy NGC 4874 and another around a different giant, NGC 4889. These two overdensities are the fossilized cores of the original subclusters, their galaxies still retaining a memory of their former allegiance billions of years after the merger was complete. It is as if two cities collided and merged, but the neighborhoods from each original downtown are still slightly distinguishable. The second, more dramatic clue is written in the hot gas. When two clusters collide, their respective clouds of million-degree plasma do not pass through each other like ghosts. They slam together with unimaginable force, creating colossal shock waves that ripple through the combined material. These shock fronts are like sonic booms on a cosmic scale, and they leave a clear signature in the X-ray glow of the gas by creating sharp edges where the temperature and density change abruptly. In Coma, astronomers have searched for these telltale shock fronts. While the overall gas appears remarkably smooth and relaxed, a sign the merger happened long ago, subtle asymmetries and temperature variations in the X-ray maps are the fading echoes of those primordial blasts. Finding them is like listening for the distant thunder of a storm that passed eons ago. The timing of this cosmic crash is one of the greatest unresolved questions. Did it happen relatively recently, say within the last 2 or 3 billion years? Or was it an event so ancient it shaped the cluster's infancy over 8 billion years ago? The evidence is contradictory. The relaxed state of the hot gas argues for an older merger, as it would have taken billions of years for the turbulent, churning plasma to settle into such a smooth, hot equilibrium. Yet the survival of certain delicate structures, like thin stellar streams, might suggest the gravitational upheaval was more recent, otherwise they would have been erased. It is a chronological puzzle where different pieces of evidence point to different chapters in the cluster's life. The number of mergers is equally mysterious. Was it a single, defining marriage between two nearly equal partners? Or was it a more complex series of acquisitions, with Coma swallowing several smaller groups over a longer period? The galaxy distribution might support a two-stage process, with a major merger followed by the steady accretion of smaller filaments. Each act of cannibalism would have injected new turbulence, reheated the gas, and altered the orbits of thousands of galaxies. The role these mergers played in shaping today's Coma cannot be overstated. That single major collision likely blasted away any cool cores, permanently heating the cluster's heart and dooming its central galaxies to a starless drought. It could have triggered the burst of star formation that created the blue intracluster stars. It almost certainly stirred the magnetic fields and re-energized the fossil radio lobes we see as ghosts. The merger did not just make the cluster bigger, it forged its very identity, determining which galaxies would survive, which would be stripped, and which would become the red and dead relics that now dominate the scene. We are left staring at the aftermath, trying to reconstruct the exact moment of impact from the scattered debris of a cosmic wreck that unfolded over 1 billion years. This hot, quiescent core presents a paradox of cosmic thermodynamics. The dense plasma at the cluster's heart, shining so brightly in X-rays, should be a cosmic radiator. According to the most straightforward physics, this gas ought to be losing its immense thermal energy at a ferocious rate, radiating it away into space as X-ray photons. As it cools, the pressure holding it up would drop, and the gas should begin to condense and flow inward toward the central galaxy in a torrential river of star fuel, a phenomenon known as a cooling flow. Simple models predict that in a cluster as massive and X-ray luminous as Coma, this cooling rain should be torrential, delivering the mass of hundreds of suns to the core every single year, sparking an epic renaissance of star formation. Yet the core is silent, hot and dry. The rain never falls, so where did all that energy go, and what is perpetually reheating the gas to defy this inevitable cooling? The leading suspect in this cosmic arson investigation is feedback from the cluster's most powerful resident, the supermassive black hole at the heart of the central galaxy. The theory is one of breathtaking self-regulation. Imagine the cycle beginning. A trickle of that cooling gas finally makes its way toward the central black hole. As the black hole feeds, it does not do so quietly. It awakens, launching jets of relativistic plasma from its poles that inflate immense bubbles in the hot gas, the very X-ray cavities we discussed earlier. The expansion of these bubbles does work on the surrounding plasma, generating shock waves and turbulence that ripple through the core, injecting heat back into the system. This outburst essentially turns on a colossal space heater, offsetting the radiative cooling and shutting off the gas supply that was feeding the black hole itself. The black hole then quiets down, the heating subsides, and the cycle is poised to begin anew over timescales of hundreds of millions of years. It is an elegant, self-correcting thermostat. But for Coma, the question is one of sufficiency and persistence. Is the energy output from its central black hole, or the collective output from black holes throughout the cluster's history, truly enough to provide a permanent balance? The evidence is mixed. The very presence of those fossil X-ray cavities proves that powerful outbursts have occurred. The energy required to carve those voids is staggering, easily enough to reheat the core for a long time. However, the black hole in NGC 4874, Coma's central giant, is currently quiet. It is not in an active feeding phase. This suggests the heating is episodic, not continuous. The cluster may swing between brief periods of violent reheating and long periods of gradual cooling, with the average over billions of years somehow maintaining the hot equilibrium we see today. Yet the complete absence of any strong cooling flow signature is telling. It implies the feedback has been remarkably effective, perhaps through a few extraordinarily powerful outbursts linked to the cluster's major merger history. That ancient collision may have funneled a vast reservoir of gas directly into the central black hole, triggering a single cataclysmic heating event that raised the core's temperature so dramatically it has not had time to cool significantly since. Alternatively, the merger's shock heating itself may have done the job, with black hole feedback acting as a secondary maintenance system. The mystery endures because we are seeing only a snapshot. We must piece together the energy budget across eons, asking if the ghostly echoes of past black hole roars, now silent, were loud enough to shout down the relentless whisper of cooling for the entire life of the cluster. This delicate, violent balance between creation and destruction, between the gravity that pulls gas in and the black hole fury that blasts it back, may be the ultimate reason the heart of this cosmic city remains a heated, starless desert. Beyond the brilliant X-ray glow and the faint radio whispers, there is a search for a far more violent light, a light that has not yet been seen. The Coma Cluster remains stubbornly dark in the highest energy part of the spectrum, the realm of gamma rays. This absence is itself a profound clue, the 24th unexplained phenomenon. Gamma rays are the universe's most energetic photons, born from its most extreme processes. If we could see them blazing from the Coma Cluster, it would be a direct signal of particle physics operating at its absolute limit. The hunt for this light is a hunt for two of the cluster's greatest ghosts, dark matter and ultra-high energy cosmic rays. The logic is compelling. If dark matter is a sea of weakly interacting particles, as most theories suggest, then those particles should occasionally collide and annihilate one another, especially in places where they are densely packed. The Coma Cluster, with its immense gravitational well and vast halo of dark matter, is one of the densest concentrations in the nearby universe. Such a collision would produce a cascade of secondary particles, which in turn would decay into gamma rays with a very specific energy signature. Detecting that signature would be the smoking gun, the first direct evidence of dark matter's particle nature. So telescopes like the Fermi Gamma Ray Space Telescope have stared at Coma for years, scanning for that telltale spike of light against the cosmic background. They have found nothing definitive. This non-detection is not a failure, it is a powerful constraint. It tells physicists that dark matter particles, if they are annihilating, must be doing so at a rate far slower than some of the more optimistic models predicted. It forces them to refine their theories, to consider particles with different masses or interaction cross-sections that would produce a fainter, perhaps undetectable, glow. The absence of gamma rays is silently rewriting the rulebook for what dark matter can and cannot be. The other potential source for this high-energy light is the violent interaction of cosmic rays with the cluster's own atmosphere. Remember those ultra-high energy particles we discussed, the cosmic bullets whose origin is a mystery. As these protons and atomic nuclei scream through the cluster, they can collide with the protons in the hot, thin intracluster plasma. These proton-proton collisions create short-lived particles called pions, which rapidly decay into gamma rays. A bright, diffuse gamma ray halo from Coma would be a clear sign that the cluster is not just a source of cosmic rays, but also a colossal trap, confining them within its gravitational grip for millions of years, allowing them to interact repeatedly and light up the entire volume. Yet again, the definitive glow is missing. This places severe limits on the efficiency of the cluster as both an accelerator and a container for these particles. It suggests that perhaps the acceleration mechanisms are not as powerful as we thought, or that the magnetic fields, while present, are not strong enough to confine the highest energy particles for the long periods needed to produce a bright gamma ray signal. They might be escaping into the wider universe too quickly, so we are left with a profound silence, the deepest darkness in the highest energy light. This quiet limit speaks volumes, whispering two contradictory possibilities. Either the dark matter particles are more elusive, more aloof than our best theories hoped, annihilating so rarely they leave no visible trace. Or the cosmic ray engines within the cluster, while capable of firing the occasional staggering bullet, are inefficient at filling the cluster with a sustained, glowing fog of secondary particles. This missing gamma ray light is a boundary, a frontier written in non-detection. It defines the edge of our current understanding, telling us that the true nature of the ghosts in this cosmic city is even more subtle, even more hidden than we dared to imagine. The silence of the missing gamma rays forces us to look beyond the cluster's present mysteries and toward its ultimate destiny. This brings us to the final, all-encompassing question, the 25th unexplained phenomenon, which is the ultimate fate of the Coma Cluster itself. We have explored its hidden mass, its violent history, and its ghostly inhabitants, but all of these are chapters in a story that has not yet ended. The cluster's future is not written in stone, but in the subtle, competing forces that govern the entire cosmos. On one hand, there is the relentless pull of gravity. The Coma Cluster is the dominant gravitational force in its region of space, and it is still growing. It sits at a dense knot in the cosmic web, and the great filaments of dark matter and galaxies that feed it are still funneling new material toward its core. In the coming billions of years, it is destined to merge with its massive neighbor, the Leo Cluster. This will not be a gentle meeting, but another catastrophic collision on an even grander scale than its ancient merger. The two giants will slowly spiral together, their thousands of galaxies mingling in a chaotic dance, their vast oceans of hot plasma slamming into one another and creating shock waves that will reverberate for eons. The result will be a new, even more monstrous structure, a supercluster in its own right, perhaps the dominant gravitational landmark for this entire sector of the universe. In this vision of the future, Coma does not die, it evolves, absorbing everything around it to become part of a titanic new entity. Yet there is a countervailing force, one that works on the largest scales of all. This is dark energy, the mysterious pressure causing the expansion of the universe to accelerate. While gravity pulls the cluster together, dark energy is pushing the very fabric of space itself apart on cosmic scales. For now, and for many billions of years to come, gravity's grip on the local structure of the Coma Cluster is far too strong for dark energy to affect it. The cluster will remain a bound, coherent object, but look far, far into the future, trillions of years from now, and the story may change. As the acceleration of the universe continues unchecked, the space between galaxy clusters will stretch at an ever-increasing rate. The cosmic filaments that feed clusters like Coma will be stretched thin and eventually severed. The cluster will become an isolated island in an ever-darkening, ever-expanding void. The most distant galaxies currently falling toward it will find their paths lengthened by the stretching of space itself, and they may never arrive. Growth will cease. Then, in the most extreme scenarios, if dark energy's strength increases over time in a phenomenon physicists call phantom energy, even the tightly bound cluster itself could be threatened. The repulsive force could grow so powerful that it overcomes the gravitational glue holding individual galaxies within the cluster. Galaxies on the outskirts would first drift away, their orbits slowly unraveling until finally, even the core galaxies are pulled apart. The great city would be dissolved, its constituent galaxies scattered into the expanding darkness, forever isolated and alone. This is the grand cosmic tension that frames every mystery we have explored. The dark matter that holds the cluster together, the violent mergers that shape it, the black holes that regulate its heart, all of these are local dramas playing out on a stage whose very size is being dictated by a deeper, unseen force. So the ultimate fate of the Coma Cluster is a question that connects its smallest ghosts to the largest mystery in physics. Will it be a builder, a kingpin in an ever-growing hierarchy of structure, or will it, in the unfathomably distant future, become a victim of the vacuum, its hard-won unity silently erased by the accelerating emptiness of space? The answer is written in the balance between two invisible giants, gravity and dark energy, whose slow motion war will determine the final shape of everything. From the invisible grip of dark matter to the silent whispers of radio ghosts, these 25 mysteries form a single, sprawling portrait of a cosmic city in flux. We have walked through the phantom streets of ultra-diffuse galaxies, witnessed the violent stripping that creates jellyfish and shuts down star formation, and felt the immense heat of a core locked in permanent drought. We have traced the magnetic fields woven through emptiness, listened for the echoes of black hole outbursts in fossil radio lobes and X-ray cavities, and counted the stolen jewels of globular clusters that crown the central giants. We have followed the faint streams of tidal debris, puzzled over the missing dwarfs and the enigmatic ultra-compact dwarfs, and read the uneven chemical story written in hot gas. We have seen how galaxy spins might align with ancient filaments, how the brightest galaxies point to larger structures, and how even the search for fleeting fast radio bursts or missing gamma rays leads us back to this crowded place. The history of catastrophic mergers hangs over it all, explaining its hot heart and shaping its destiny, a destiny caught between the binding force of gravity and the relentless push of dark energy. The Coma Cluster is far more than a collection of ancient galaxies. It is a natural laboratory on a galactic scale, Every unexplained phenomenon, from the largest missing mass to the faintest blue star in the void, is a precise experiment already in progress. Each mystery is a clue left by the universe itself, a question about the nature of dark matter, the behavior of gravity, the birth and death of galaxies, and the fundamental forces that sculpt reality across billions of light years. The answers are not here yet, but the tools to find them are in the telescopes that map its every wavelength and the theories that strive to explain its every contradiction. This cosmic city, floating over 300 million light-years away, is a mirror held up to our own curiosity. Its puzzles remind us that the universe is stranger, more dynamic, and more interconnected than we often dare to suppose. So keep looking up and follow the journey of discovery as it unfolds. The next great revelation about dark matter or cosmic magnetism or the fate of all structure might very well come from the silent, swirling depths of the Coma Cluster.